In this section, let's look at the line processor grep, which allows us to process items from lines of files that are of interest to us, such as log files or otherwise. So let's unlock the screen and continue our studies of this ever so important and ubiquitous tool. So grep. Grep is a regular expressions line processor. So processes lines using regular expressions, beginning with, but not limited to, simple regular expressions such as searching for characters that are of interest, such as keywords from documents, and also including traditional regular expression meta characters. So using regular expressions, which means normal and meta characters. And it returns entire lines when keywords are matched or keyword is matched. So the entire line will be returned, which means if you need further parsing, such as the extraction of specific columns, then you'll need to use grep in conjunction with a tool such as awk, for example. So it searches for text and for those keywords that are indicated in various text files. So it's a text regular expressions processor. Now let's set up some tasks for us to do to see how grep carries out its magic. So the first thing for us is to create some content. So create file with content. And as an example, we'll generate a file naming it grep.test.txt, and we'll store in it some useful information. Now, as opposed to using a different editor such as Nano from the shell, we can just create a new tab in this window and generate the content and save it. So let's include some simple entries. For example, here's a line which contains the word Linux, and then the term Red Hat Linux, Linux 2011, and Linux CBT. So 4 items that are worth grepping. Let's save the changes. We'll call this grep.test.txt. Of course, it's in your docs subdirectory. So there are some strings that are of interest to us. Linux, Red Hat Linux, Linux 2011, Linux CBT. How can grep be used to parse these simple data? So for example, if we grep simply Linux from grep.test.txt, wherever the word Linux in the case that's presented occurs in the document will cause the entire line to be returned. So this returns all matches for the case upper L, lowercase li, or lowercase I nux. So the case matches precisely unless you indicate the I option, which is case or means case insensitive. So grep Linux from grep.test.txt, from what we can tell, should return every line as each line contains the word Linux. So from a shell, let's confirm that is the case. And indeed 4 lines were returned. To count the lines for larger documents, just pipe the output into word count with the L option, which counts lines, and indeed 4 options, 4 values, 4 results were returned. So in each case it returns. Now what if we include Linux in lowercase, for example, or even mixed case? Let's see how that influences the grep search. And indeed it still returns 4 results. Let's see what those results are. And notice it doesn't include the lowercase Linux because the grep search is case sensitive. So let's just note that as well, that by default it is case sensitive. So 3 searches are case sensitive by default, which also means that you can turn on case insensitivity if you use an option. So use -I to enable case insensitivity. And case insensitivity is an option that's available with all regular expressions tools, such as Perl, grep, awk, sed, etc. So you can always search using case insensitive searches for strings. So now, when we research with the case insensitive option, that's -I, it will return that additional record, and when we pipe the output to word count with the list option, 5 records have been returned. So, as a separate task, perform queries, and one is to grep case sensitively, and another is to grep case insensitively for the keyword Linux from grep.test.text returns all cases of the word Linux, which means if we include mixed case, it should work as well. So let's try that out. And return to the shell with a case-insensitive search, and it returns 6 options. And there we see the mixed case. And if we also mix the case and include perhaps another string, that will be returned as well, because as mentioned, grep returns entire lines, which is often desirable when parsing large documents, such as log files for specific records. So you perform a case-insensitive search using the I option. Now, there are a number of other ways you may use grep. For example, you can grep for numeric values. For example, grep 2, because one of our records, if not 2 of the records, contain numbers, 2011 for example. So you can grep the most unique portion of those numeric values and have it returned. So grep 2 doesn't necessarily mean, or does not mean, to grep the second line. It means to grep the document searching for lines that contain the number 2. So grep 2, we'll place it between double quotes, although not mandatory, test.text, just convention, and returns all lines containing the number 2. And this includes whether the line includes a number 2 juxtaposed with other characters without spaces or with spaces. So long as 2 exists somewhere on the line, grep will find it. So let's try and see what happens. And there are the 2 lines that contain the number 2, regardless of the placement on the line. Now that leads us to some other types of searches where we get into meta characters. So meta characters, some simple meta characters. Now meta characters in regular expressions allow us to perform searches based on meaningful string combinations and positions. So we're able to use these symbols to indicate that we are looking for text in specific places. And for example, if we perform a search where 2011 must end the line, that will extract specific records. So for example, let's grep 2011 from grep.test.text. Now in and of itself, this will pull both lines that include 2011 because they exist in various places on the line. Now supposing we wanted lines that terminate with 2011 because those records are of interest to us, that's where meta characters can be quite helpful. So if we instruct grep to perform a search where 2011 terminates the line using a $ symbol, then it'll return just those records. Now in our case, that means 2 records. But as the document grows more complex, then the results will be varied. So returns lines that terminate with 2011. Let's try this out. Again, this can be quite useful for large parse routines. And this will use a meta character. So notice it's pulled both lines, but you don't see the power of it until you introduce new content. So let's navigate to grep.test.text and include, let's say, Linux CBT 2011 edition. So now 2011 doesn't terminate this line, which means it should not be returned by the recent search, and it was not returned. So only 2 lines were returned. Because again, in this example, 2011 does not terminate the line. So the $ meta character across regular expressions tools, whether Perl, grep, awk, sed, means to search for content at the end of the line. Let's just note that $ means to search for character or content at the end of the line, which also means there must be a way to search for content at the beginning of the line, and certainly there is. So the character is the tilde character, and you can use single quotes if you'd like, but since we've used single quotes to enclose what you should execute literally, we'll use double quotes within, unless there are cases where double quotes will not preserve the string literally. So let's look at our content to see what's of interest from the beginning of the line. Supposing we wanted lines that contain, let's say, Linux at the beginning of the line. That, of course, will return the bulk of the lines, including lines containing Linux CBT, as Linux is a part of Linux CBT. So, using the caret symbol, Shift-6, followed by Linux, will do the trick. Now, by default, this will not perform a case-insensitive search. In other words, it's case-sensitive. So let's just note grep.test.text, close with single quotes, and indicate that this returns lines beginning with Linux, and it is sensitive. So let's just note case-sensitive. Let's try this search out to see what happens. So again, if you're looking for content that begins a particular line with strings or a string of interest, then indeed this will do the trick. Let's tab this out, tab completion, and there are the lines beginning with Linux. Now note that the line containing, or lines containing, variations on the case were not returned, including lowercase Linux and mixed case Linux lines. Just the line with the appropriate case that was indicated, lines that with the appropriate case indicated were returned, which means if you also combine the case insensitive option, you'll see those additional lines. So just alter this search with the case insensitive option and it will do the trick. -I. Let's just copy and paste that to indicate, to make sure that that's clear, and tack on a -I, and now the search is case insensitive, which is more desirable. So that means for the most part, when you use grep, you'll turn on the I option to search for content, because you can't always be assured that the content you're searching for is represented with a fixed case. Oftentimes applications log consistently, but sometimes there are discrepancies causing you to vary your queries. Now these meta characters, $ and caret, are called anchor tags. So note, caret and $ are anchor tags because they anchor the string that we're looking for, either the beginning in the case of caret or at the end in the case of $. So those are some meta characters. There are of course other meta characters such as .* to search for all matching characters that's of interest, which is like a wildcard used from the shell, for example. So let's construct another option. Let's search for all lines beginning with L and anything following is acceptable from grep.test.text. This is another loose way of specifying a wildcard grep query using .*. .* in regular expressions means any match after that particular item. And notice it returns all lines containing, in this case, L, wherever it exists on the line. Now, what if a line does not contain L? Let's create such a line. Let's label this line test line 1. In fact, it contains L, so let's just call it test 1, for example. Let's see what happens when we search for L.*. And notice, of course, it doesn't return because it must begin with an L, otherwise it will not. Now, what if L doesn't begin the line? So let's say we've got test 1 or test line 1, for example. So L doesn't begin the line, but we haven't indicated the caret symbol to indicate that L must begin the line, so test line 1 is still returned. So long as the match is performed somewhere in the line, it's returned, which means if you want L to begin the line, you can anchor it with the caret meta character, and that ensures that L must begin the line. You could also ensure that whatever follows the L ends the line. So let's just note what this particular query does, and this searches for L followed by any characters, which brings up another point. And let's just also include that the same query with an anchor tag to begin the line, L.star, grep.test.text, searches for L where begins the line, etc. Which brings up another point that we almost alluded to. So supposing we have a line that contains, in this case, since we're searching for L.star, what if the line just contains L? So let's see what happens here, meaning no characters following L. So let's see how the grep search is performed. So in that case, in the last line, L begins the line, so the caret will work. Now what happens with the remainder of the search? Notice that L is still returned, so which brings some confusion to the mix, because .star means any amount of characters following the literal character L. But it also means 0 or more. So let's just note that .star means 0 or more matches, which means that if there isn't a match, that's fine. And if there is a match, that's also fine. So in the case of L by itself, there is nothing following the L, but the line was still returned. So that works as well. Now what if we had L followed by a space, then INUX CBT? Again, this will match, because after the L is a space, a non-printing character, and a series of characters, INUX CBT. Let's try this out to see what happens. So long as L begins the line, it will be returned. So L is returned. The space is a character, albeit a non-printing character, followed by INUX CBT. So that's returned as well. Now if we drop the caret symbol, certainly that last line will not be returned, because it actually doesn't start the line, or will be returned because it doesn't have to start the line, which means if we alter the content to include, let's say, test L space INUX CBT, this will be returned without the caret, but not with the caret. So let's try that. And there it is without the caret. And then with the caret, it's not returned because it doesn't begin the line. Again, the anchor tag is of the utmost importance. And similarly, the other anchor tag, $, indicates that any characters may end the line. So any of the characters specified after L will suffice when terminating the line. Now you could search for other combinations, such as L.star followed by a series of characters end the line. So for example, L.star CBT. So grep, begin the line with L, make it case insensitive, give me any number of characters so long as it ends with CBT. This will ensure that the line ends with CBT from grep.test.text. Let's see what happens here. Searches where L begins the line and T ends the line. In fact, it's actually CBT, since we're mandating by literally specifying CBT. So CBT has to end the line. And before we execute the query, let's just confirm the content that we're searching against. So L must begin the line, CBT must end the line. That means this line will be returned, because .star will take care of everything up to, but not including CBT, and then CBT will literally take care of that. Although without the CBT, the .star would cover CBT. So this line will certainly be returned, and it's a case-insensitive search, this line will be returned. So far it looks like 2 lines will be returned. Let's try this. So long as we have the $ at the end, indeed, 2 lines are returned. Now, let's include a case-insensitive mix of that. And we'll put it as lowercase. And it is case-insensitive on the search, and that line's returned as well. Now, what if we included a single space at the end of the line? This happens often when editing documents, and it often happens inadvertently. So we introduce characters, especially non-printing characters like tab and space, for example, unbeknownst to us. It happens all the time. So in this case, notice that 2 lines were still returned. So why isn't this last line returned? Because CBT doesn't end the line. There is actually a space. And because there's a space, it doesn't show up. Now, what if we include a space in the search? Then the line that includes the space which terminates the line is returned. The other lines aren't because they don't end with a space. Again, if we move the cursor, notice below in gedit, line 13, column 9. Column 10. So between 9 and 10 there's a space. But for the other lines that are of interest, for example this one, column 10, there is no column 11. It moves to the next line. And above this line, ditto. Column 9, looking in this section of course, when you move to the right with the cursor it moves you to the next line, which means there is no additional information. So let's just include that as an optional search. No big deal, but nonetheless might still be helpful to know that if you anchor your search, let's say $CBT space $ grep.test.text. We're kind of mixing and matching single and double quotes, but nonetheless from the command line it'll be interpolated properly. So search is where L begins the line and space ends the line, which also begs a question. Does that mean any number of spaces? So let's look at this last line here. So Linux CBT 1 space matches the search because we've literally specified 1 space. Now let's specify another space and then save the changes. So T ends at the 9th column, 10, 11 are spaces. So let's search. Every time you make changes, make sure you save. And notice that it doesn't work because it's searching for a single space. Now we could introduce .*, for example, in the search, and this will return the lines that contain a variety of options, including 1 or more spaces, 0 or more spaces, as well as other characters. So you can place multiple wildcards to enhance your search, if so be it, or if that's what seems to work for your environment. This should be option G here. So let's just note that grep I index at L CBT, and again .*. You can reuse these characters as many times as you'd like, followed by $, will capture those items. Now if you want to capture space definitely at the end, you could do .* space $, grep.test.text, and it does just like above, searches where, let's just correct this here, searches where L begins the line, and again space ends the line with variations between, or more variations between than before. So this search, let's just try again. In this instance, we will accept any characters after CBT that end the line, but if you insist that a space ends the line, then do it that way. And this will pick up a variety of values, including values that include multiple spaces. So for example, this line Linux CBT now terminates with 2 spaces. We simply need to move the cursor twice to the right to realize it. Let's add 5 spaces. So we're moving from column 9 all the way through 15, so it actually has 6 spaces. The grep search will still get the line, because again, so long as the line begins with an L, whether upper or lower, followed by any number of characters, then CBT, followed by 0 or more characters, followed by space. Now the 0 or more characters also includes space. So this dot star that you're seeing here, or you see here, is responsible for capturing n number of spaces or n number of characters after CBT, which is why it's picking up a variable amount of spaces after. So that's why we specify it in that particular case, to be able to pick up on a variety of characters after. Now there's still other types of meta characters that are of interest. So for example, character classes. Supposing you wanted to search for strings using a logical or using some sort of ORing, a logical ORing built in. That's where character classes can help you, because they'll allow you to search for item 1 or item 2. So let's look at our content to see what may be of interest. So supposing, for example, we wanted to search for lines that contain the word red or 2011. So that should return this line, this line, this line, and this line. So 4 lines. So let's see how we construct that using character classes. So grep case insensitively, and between square brackets will indicate the character classes using a pipe to separate the characters that are of interest. So let's search for red or 2011 from grep.test.text. This uses character classes. Character classes allow us to search using a class of characters, which may include alpha or numeric or meta characters. So let's see what happens when we perform this search. Let's just check our quoting here. One extra quote. Now in this case, what's happening is that it isn't treating the full word red as a match for all lines. It's looking at each character, determining whether or not the line contains it. So for example, if the line contains an R upper or lower, it matches. Same for E. So in the case of test, line 1, test, so on and so forth. D, wherever D exists, it exists in this line. Or 2, 0, 1, 1. So that's why test line 1 came back, because 1 is a part of it. So with this character class search, what happens is that it searches each character in search of a match. But it could be used as a way to extract specific lines. Like for example, if you know there's only one line that contains an R, this one, you could search for R, or let's say only specific lines contain 2 or 0. You could do that as well. Now a number of other options are supported with grep, as well as the other standard regular expressions parsers like awk and sed. Also grep, awk, and sed support or share the same regular expressions syntax. So let's just note that as a feature as well, that if you learn one, you've in essence learned the regular expressions components of the rest. So shares regexes or regular expressions with awk and sed, which are 2 other important tools that we'll be looking at. Now oftentimes in production settings, you're forced or required to use grep with log files to search for content that's of interest. So let's SU in and navigate to var log. And messages tends to contain all of the system messages. In this case, the file is rather slim. Let's see what's in this directory. And we have a backup file. Let's see its type. And it is text. So this file can be grepped for items of specific interest. So for example, supposing you wanted to see events from a specific date that concern the kernel, Notice as we scroll through the document, most of the dates, all of the dates so far are January 6th, and then now it moves into January 7th. Let's tail the contents of this file to see where it ends. So it runs all the way through January 9th. So supposing we wanted to extract items from January 9th that pertain to the kernel. So this is where you could use grep in a simple fashion. So for example, let's extract this string because it's of interest, January space 9th, exactly as it's presented, since syslog is logging in the file consistently. So as a separate task, parse system log. So case insensitive search for the following string. January space, in fact it's more than one space, it's two spaces, and that's important unless you use a regular expression. So January 9th, for example. Now we know that JAN begins the line, so that's important. And we know that 9 is the last section of the string, but it doesn't end the line. So let's grep January 9th from var log messages. Now, of course, this will dump all items pertaining to January 9th, not particularly any specific daemon options like kernel options, for example. So here are all the options from it, but we don't want from var log messages. We want from the other file, messages-2011-0109. So let's copy this because it contains more items. And update our notes. So this is the file that we're interested in parsing. So this is going to return to stout all packets from the 9th. Let's see how many lines there were. 48 lines, not a big deal. So here are the lines from the 9th. 48 lines we can quickly parse through now. We might be curious, so let's say it's 48,000 lines on a busy system. Are there any kernel entries that are of interest to us? So piping the output again into grep, searching for the keyword kernel will allow us to determine anything that may have pertained to the kernel. In this case, it was just one instance on the 9th. So we've been able to get the 9th. So nothing major happened other than kernel logging stopped, which means the system was brought down. How about on the 8th of January? From the same file, since log rotate rotates the items, nothing that's of interest. Let's look for the 7th, and so on. So there you see the 7th contains more items. Let's WCL. So on the 7th, there were 468 items from the kernel of all types. Let's include this search to show that it's an effective way of parsing the log file in search of interesting items. So in between single quotes, let's terminate this with single quotes as well. So this parses for items for January 7th, which also begs the question, could we use character classes to parse items from multiple dates, for example? So the question then would be, well, why be restricted to simply January 7th? Why not search using character classes for perhaps the 8th and the 9th? Indeed, there's nothing to prevent you from doing that. So that's one example where character classes can be helpful. So let's copy this search and paste it below as task C and mark it up. So when we search our documents, we search as variably as possible. We're now looking for, let's say, items from the 8th and the 9th. So this will parse 8th and 9th, and if you're not comfortable about the space between January and the character class left bracket, then just include .star with no spaces. So this searches for either date. So searches for both January 8th, and let's just include the additional space, and January 9th. Again, to alter the search to account for a variable number of spaces, you could use .star, for example. Only caveat is that .star would pick up any items after including in this case January 7th, but it also gets the 9th and the 8th. So that's one issue to be concerned about. You could also search for spaces using the space meta character. So there are a number of ways in which you may perform the search. But again, you can grep and then pipe the output again into grep. And if you need further filtration, you can grep again. So grepping gives us 8th and 9th. And then you could further grep, let's say, for something of a specific instance. So let's look for the 7th and the 8th. And supposing we wanted to see RPC, so grep again, case insensitive RPC. And there we see across the 7th and the 8th entries related to remote procedure calls. Or let's say items pertaining to the kernel crashing or IP tables or Ethernet 0. Let's look for items from Ethernet 0. It's always good to protect your items with quotes. So let's look for Ethernet 0. So across the 7th and the 8th, there were 2 entries, both on the 7th, concerning Ethernet 0. And this shows that the link came up in fast Ethernet full duplex mode with its address information and MAC address information and the interrupt and so on. So grep is as old as Unix, which means it's as old as Linux, and is an important tool in helping you to search for information across the system that lie in text files. There are a number of other options. Just run grep with the help option, and you'll see those useful options, such as the ability to search recursively, for example, for content, meaning descending into various directories in search of content of interest. So that's a little bit about grep. Let's move on to some of the other important tools.